Today I'm going to be presenting breakthrough measurements for determining diffusivity using the zero-length column method. Thank you all for attending, and I look forward to many interesting discussions at the end of this talk. So before we begin, first we need to kind of talk a little bit about what is breakthrough analysis. So breakthrough is the collection of adsorption data over time by measuring concentration of the exit gas compared to the inlet gas concentration. So it's a dynamic system, very different from a lot of our systems which tend to be static. There's actually gas flows, potentially multiple different gases that are flowing at one single point in time. Additionally, adsorption can be physisorption or chemisorption, so there's not necessarily a distinction like there is in some other techniques. Breakthrough can consist of either physisorption or chemisorption processes for the actual adsorption. More or less what's happening during a breakthrough experiment is you're charging your sample column with some sort of inlet gas that may contain some inerts, some adsorption gas, maybe there are some contaminants in there as well. And then in the sample column, the adsorbent material adsorbs the target analysis gas, and then the rest of the gases proceed through the column. And then what happens is a mass spectrometer or other device measures the outlet concentration, and the inlet concentration is known. The outlet concentration is what you're determining, and then kind of the difference in concentration of your adsorbing species is the result of adsorption in the sample column. So next I'd like to talk a little bit about some of the differences between dynamic systems and static adsorption systems. So a dynamic system, as I've talked about previously, is something like breakthrough analysis, whereas static adsorption is something that you might use in a 3-flex or a TriStar or another instrument that we sell. So in dynamic adsorption, there's going to be a continual gas flow. So like I said before, there may be multiple species present, one or more adsorbing gases. There may be some vapors as well as inert gases. Maybe there's some contaminants in your gas stream, kind of helping mimic those actual real-world process conditions that you might see. Concentration is typically measured using something like a mass spectrometer, FTIR, or individual sensors. So in a lot of cases, dynamic adsorption is kind of the next step after you've kind of finished characterizing your materials, is to assess the adsorption performance in conditions that are more similar to what you'd find in an industrial process. For static adsorption, gas flows, from the cylinder to the manifold, and then from the manifold into the sample tube at set times through valves, and there's particularly dosing intervals to be able to dose and collect in data, which is presented in the form of an isotherm. So one particular gas is measured at a time. So in our static adsorption experiments, there are not multiple gases, there's just one gas. Additionally, there's no inert present either, so if you're doing anything like vapor phase, you're specifically dosing the vapor as a gas, and there's no sort of carrier gas, which is one of the main differences between static and dynamic adsorption experiments, is the presence of potentially multiple gases, including inert gases. Adsorption is also determined using the ideal gas law with the compressibility factor to account for the non-ideal behavior of gases. More or less kind of going back to kind of like initial gen chem, very similar to the ideal gas law, PV equals nRT, for being able to determine the number of moles of gas that's adsorbed at one particular point in time. So there's many differences between dynamic adsorption and static adsorption, and how you use the techniques can give you valuable data about your materials and being able to assess them for kind of industrial applications. So the next question you might ask is, okay, well, why do I care about breakthrough? Well, breakthrough is a powerful technique because it allows you to mimic process conditions and gas conditions that you may find in industrial processes. You can also collect multi-component data using a mass spectrometer, FTIR, or individual gas sensors. And in most cases, in industrial processes, there's not one single component in the mixture of gases that you're looking to capture. There may be multiple different components. They may interfere with some of your adsorption sites, so you need to be able to take that into account, which is not something that can be done using, these single component analyses, which is why you might want to move on to using breakthrough or some kind of multi-component analysis procedure. Breakthrough is applicable to a variety of different industries, such as oil and gas, energy, novel adsorbent materials, membranes, polymers, and separations. So when developing a new material, often you may start with kind of a static adsorption for characterization, kind of being able to estimate the adsorption performance and being able to tell, okay, is this a good candidate material for my real-world application? After that, you may move to breakthrough analysis for kind of assessing it in these more real-world conditions to see if it kind of lives up to your expectations based on what it could achieve in the static environment. So next we're going to talk a little bit more about processing a sample for breakthrough analysis. So processing a sample in sample preparation in general is key to ensure that you get good breakthrough results. Like all flow-through measurements, it's ideal to limit both pressure drop and mass transfer limitations. So since you actually have gases moving in a dynamic system, it's very important to ensure that you have the appropriate flow rates and there's not any restrictions of flows. And in addition, you also want to try and limit mass transfer limitations as much as possible and have appropriately sized particles to limit these effects. So samples are generally activated under gas flow while also heating the sample. So you might be using some sort of purge, nitrogen, argon, or helium gas stream to remove kind of any adsorbed species from the surface of your adsorbent material. After that, you'll then conduct breakthrough analysis. And generally, part of breakthrough analysis is regeneration and cycling to determine, the lifetime of your adsorbent or how many cycles it can last for to determine the cyclic stability. So after you've prepared your sample, you've collected your data, the data will be shown in something typically called a breakthrough curve. And a breakthrough curve can be broken down into three components. The first step shown in blue there, where essentially all of your adsorbing gas that's entering your column is being adsorbed, so the exit concentration that we measure is approximately 0. Eventually you'll hit the green zone where breakthrough occurs. This is where you first start detecting that adsorbing gas concentration, and it will steadily rise until eventually you reach saturation. So the yellow zone shows saturation. That's where essentially the gases that you're putting into the column equal the gases that you're putting out of the column, meaning that your column has reached the maximum capacity for the gas that it can absorb. So to kind of break this down, you can imagine in our system here, you have a sample column and you're flowing in multiple different adsorbing gases and inert gases. And during that complete adsorption phase, what's happening is both gases are entering the column, but only one is leaving, the inert gas, because it's not adsorbed. And the adsorbing gas concentration that will be measured in your outlet detector will be 0 because it is completely adsorbed by the sample. During breakthrough, you're still flowing those same gases in at the same concentrations, the same flow rates, but the gas that's coming out, you're getting the same flow rate of that inert gas, and the amount of adsorbing gas that's breaking through the column and exiting out to your detector is slowly increasing over time. When saturation is reached, you have the same flow rate going in, and then now it matches in that same flow rate of gases leaving the column for both the adsorbing gas and the inert gas. So once you've collected this data, how is it analyzed? And the data is analyzed by solving the breakthrough equation, which is shown on the right-hand side there, where the quantity adsorbed of some adsorbing gas I is equal to an integral from time 0 to the time when saturation was reached, and then you multiply that by a normalization of the concentration and multiply that by the flow rate of your adsorbing gas and then integrate over time. So before analyzing the data, a 0 point needs to be determined. So unlike in static measurements, here you have flow, and because you have flow, there's going to be some delay in your signal from when it's actually adsorbing into the column to when it exits the column, goes through the gas lines, and goes out to the detector. So that there's going to be a slight time delay for that travel time of the gas. This travel time delay is commonly referred to as the dead time of the sample column, which is essentially how long it takes from when it exits the column to it to actually reach the detector. Overall, when you're analyzing the data and solving this equation, the quantity of gas adsorbed by the adsorbent is equal to the area left of the breakthrough curve. So seeing this kind of as a graphic here, you can imagine that you start flowing an inert and an adsorbing gas, maybe somewhere around time 10 in this example, and the inert gas, it breaks through almost immediately, and it has a very sharp, steep breakthrough, which is what you'd expect because it's not adsorbing, so it will break through completely and almost all at the same time. The adsorbate gas is going to break through more slowly. There may be some mass transfer. There's adsorption that's going to continue going on as the bed reaches further saturation. So it's going to be a little bit later on that you get the breakthrough of your adsorbing gas. The area between these two curves shown in red is going to be equal to the quantity adsorbed, and as well as the solution to the breakthrough equation. So for today's talk, we're going to be focusing on the zero-length column method. So the zero-length column method is a method to determine the diffusivity of an adsorbent gas in your sample. So previously, we've been talking about breakthrough analysis and adsorption, but for the zero-length column method, we actually care a lot more about desorption, or the desorption of our gas. And in this technique, what happens is you collect a breakthrough experiment as normal. Typically, you will do it with a very low concentration of your adsorbing gas. And then at the end of the experiment, you're going to start some sort of purge, and you're going to have a trigger, much like you do for the adsorption process, where you may use some inert. In this case, mass 40 or argon is our inert that we're using for both the start of our breakthrough experiments and the end of our breakthrough experiments. And we can see that the sharp increase and subsequent decrease at the end of the experiment is very sharp for argon, whereas when we look at our mass 44 here, the decrease is more gradual. So what this signifies is that, the propane, in this case, leaving our adsorbed particle much more slowly, kind of slowly over time, and bleeding out of the system because there are some sort of mass transfer limitations. There's some diffusion out of that particle for the desorption of the originally adsorbing gas. So the reason it's called the zero-length column method is because ideally in this method, you want to assume that you have a infinitely small amount of material loaded in the column. Having a zero-length column has the benefit of, if you can imagine that if it's zero length, then there can be no additional kind of readsorption of your initial adsorbing species. So it's not going to, desorb from one particle to later readsorb to a later particle further down in the sample column. It's a zero-length column. So for the experimental setup, you're going to pass your adsorbing gas through the column at a low concentration until saturation is reached. Essentially, you're going to collect a breakthrough measurement. You'll then start flowing an inert gas through the column and monitor the desorption of the adsorbate gas that was initially adsorbed. So in this case, all that you're going to be flowing through is going to be your inert gas, and then your adsorbing gas that had previously adsorbed is going to start flowing out. The diffusivity should be independent of your inert gas flow rate, and if the diffusivity is independent of the flow rate, it means that your mass transfer limited and the ZLC technique applies. If diffusivity is not independent, then you likely have some sort of other dependence, such as kinetic limitations in your process, and the ZLC technique does not apply. So if there's some kind of strong adsorption interactions or kinetics that are in this process, you're not going to be able to get accurate diffusional data because there's going to be other components contributing to how fast the desorption process occurs that will limit the applicability of this technique. So for the ZLC method, as I mentioned before, we're mainly looking at the desorption end. We still need to do the adsorption, obviously, but for the data analysis portion, we're primarily concerned with desorption. Additionally, we're going to look to calculate the diffusivity of gas, leaving the sample when subject to an inert gas flow following adsorption. So no heat will be applied to the sample, so the only driving force for desorption will be passing that inert through the sample and the slow diffusion of our adsorbing gas out to that purge gas stream. The technique is valid for both single component and multi-component adsorption. So today I'm going to be only showing single component data, so there's only going to be one adsorbing species and inert gases. But in theory, you could apply this to multiple adsorbing gases, and it may be useful to apply it to multiple adsorbing gases if you have multiple species in your process. Additionally, if it's tested on a single particle or very small amount of material, there will be no readsorption later in the column, so you don't have to account for the fact that a gas could leave one particle and enter another particle to kind of readsorb before it finally desorbs again later on in the ZLC experiment. So typically when you're solving, you'll plot a ZLC response curve, and the equation for that is shown here in spherical coordinates. Spherical coordinates greatly simplifies the math for being able to determine what the diffusivity is, because you only need to consider diffusion kind of outward in that radial direction for kind of the diffusion length. It should yield a linear response near time t, t equal to 0. The shape and slope should also be independent of the purge gas flow rate. So plotting the natural log of C over C naught versus time should yield a linear line, and the slope of this line is involved in solving for the diffusivity of the exiting gas. The equation that's shown above, as I mentioned, is specifically for spherical particles, and as I said before, the mathematics get a lot more complicated if you don't have spherical particles, and that's not something that I'm going to cover. For this talk, I'm going to be focusing specifically on spherical particles because it greatly simplifies the math. So in this experiment, I'm going to analyze two different samples for propane adsorption on the BTA and collect these ZLC response curves. So the two materials that I'm going to be looking at are zeolite 13X and zeolite 5A. So luckily, both of these samples are spherical and have very consistent diameters across multiple different particles. So I'm using kind of conventional materials that you could acquire from a number of different sources and suppliers, and this greatly simplifies the math. So for the diameter of the different particles, I assess them using calipers that are accurate to 1/100th of a millimeter. For the sample activation, I activated samples in situ on the BTA prior to analysis by flowing nitrogen at 90 degrees C for 1 hour, followed by flowing at 300 degrees C for an additional 4 hours. For the breakthrough adsorption portion, they were collected using flow rates of 1 standard cubic centimeter a minute for our argon, which is our tracer gas in this experiment, 1 standard cubic centimeter a minute of propane, which is our adsorbing gas, and then additionally 18 standard cubic centimeters a minute of nitrogen gas, which is our carrier gas in this case. For our response curves, nitrogen was used as the purge gas at 40 standard cubic centimeters a minute, and once again, argon acts as a trigger since we shut that gas off at the end of the breakthrough experiment, and we're able to see the slow bleed out of propane over time since it has to slowly diffuse out of the particle that it adsorbed in previously. So shown here are some breakthrough curves for our zeolite 5A. So there's 3 triplicate data set here for the zeolite 5A breakthrough curve showing the adsorption and then later the desorption. And we can clearly see here that both on adsorption and desorption, our mass 40 for our argon is a very sharp, steep incline at the beginning, and then a sharp decrease or drop at 35 minutes, where we shut off our breakthrough experiment. And then we can see our mass 44 or propane, which adsorbs more slowly. And then also we can see how it much more slowly leaves the sample column and exits to the detector following shutoff at that 35-minute time interval. The delayed response is due to the adsorption of propane. We can see that no argon is adsorbed. Roughly when we start the experiment at that 5-minute mark, there's complete breakthrough of argon almost immediately. Looking at the desorption branch, we kind of see a similar thing where there is the immediate drop in the argon concentration at 35 minutes, and then there's a delayed response due to the desorption of propane out of the particle. Looking at this for our zeolite 13X, we have very similar looking breakthrough curves where we can see once again, we have very, very sharp breakthrough of our argon, our inert tracer gas, which is what we would expect at roughly 5 minutes, and then a sharp decrease again at 35 minutes. We can also see that for our propane, there is a delayed response for the adsorption of propane, which is what we'd expect since adsorption of propane is occurring, and no argon is adsorbed. For our desorption, there's also a delayed response after 35 minutes where the propane needs to slowly diffuse out of our particles. So plotted here are the adsorption capacities for these 6 experiments, 3 for our zeolite 5A and 3 for our zeolite 13X. So our 5A adsorbed, somewhere in the realm of 34 to 37 cubic centimeters per gram STP of propane, and our zeolite 13X adsorbed roughly 56 to 57 cubic centimeters per gram STP of our propane. Next, we'll look at our ZLC response curves for our zeolite 5A. So shown at the top right, we have our diffusivity calculation, where our diffusivity is equal to the slope times the radius squared of our particle divided by pi, which is valid for these spherical particles. We're then able to see our ZLC response curves, which is the natural log of our C over C naught concentration versus time on the x-axis. We can see that we have fairly linear response curves, which is a good sign that we likely are in the kind of mass transfer limited regime for these samples. And then we're able to use treadline fit in Excel to get slopes for these 3 separate experiments that we conducted. After that, we'll be able to calculate the diffusivities, which we'll show on a later slide. We can do the same thing for zeolite 13X, using the exact same equation. We can see here that, once again, our ZLC response curves are very linear, and we're able to trendline fit these for our ln of C over C naught versus time for our zeolite 13X. The particle size was quite similar between the zeolite 13X and the 5A. The 13X is slightly larger, but comparing the slopes of 13X versus our 5A, we can see that we have a little bit larger magnitude slopes for our zeolite 13X. And moving on to our diffusivities, we can see that shown here are diffusivities of zeolite 5A and zeolite 13X for the diffusivity of propane in these two materials. The diffusivity of zeolite 5A is roughly, somewhere between 4.4 and 4.9 meters squared per second times 10 to the minus 8 versus 13X, which is roughly double the diffusivity that was measured for zeolite 5A. This makes sense based on the pore size of 5A versus 13X. So the pores of 5A are smaller than 13X, so we would expect that there would be faster diffusion through the larger pores of our zeolite 13X, which is what we saw in our experiments. So in conclusion, the ZLC technique is very powerful and give you a lot of valuable kinetic information, kind of looking at the diffusivities of some sort of adsorbing gas in your sample. Sample sizing is very important, and having the minimum sample quantity or as close as you can get to that 0 column length while still being able to obtain reasonable adsorption, desorption data is important. Additionally, shape is very important. So for the samples I shared today, they're very small formed pellets. However, the math gets a lot more complex if you move to coordinates outside of those spherical pellets. So in this study, the diffusivity of propane in zeolite 5A and 13X was measured using the ZLC technique, and we saw that zeolite 13X showed about a 2 times increase in diffusivity compared to 5A, which makes sense when you consider the pore sizes of zeolite 13X and zeolite 5A.